Good today. Okay, so what are we working on? What are we working towards, rather? What are we trying to do? Can you not remember that? Like I said, cutting planes last week. So that's what we're trying to do. And we were looking at some possible ways how you devise what we call valid inequalities. Okay, so a valid inequality is one which is satisfied. So we've got a linear program. This one doesn't have the objective because the objective has nothing to do with. Does have something to do with it, but not with the what valid inequalities are. For that, you just need the constraints. And so we're trying to find new constraints that are satisfied by all the integer solutions. And the idea is to find, well, the idea will be later. Okay, so this is the main thing. And why do we want it? Well, we want it because if we keep adding these new constraints and they keep cutting off some solution might have, then in the end we can end up perhaps with just the integer solutions in the corners. And then when we find a basic feasible solution of the LP relaxation with the added constraints, it gives us an integer solution. And that integer solution is going to be the optimal solution that we're looking for. Okay, so that's the main basic idea here. And we looked at some ways to do it last week, and that's what we're continuing to do. Okay, so this is going to be the main idea of the algorithm that we're learning today. Is you take multiples of some of the constraints that you were given in the beginning. So for example, okay, and now you have absolutely no idea why I want to times this one by 2/7 and this one by 37/63 and this one by 0. Okay, but I do. And I'll tell you in a bit how you come up with things that lead to those numbers. So when you add them all together, what you get is 2x1 plus apparently 1/63 x2 is less than or equal to 121 divided by 21. Okay. Is this inequality satisfied by all the integer feasible solutions to that? Yes, because it's just times some of them, add them together. So if they satisfy each of the three constraints, even without being integer or anything, they have to satisfy this. Okay, so if they satisfy this, it's called a valid inequality. So this is a valid inequality. Okay, now the trick we learned last week was, if we have a valid inequality like this, what we can do is round down all these coefficients for the x's. And this is still going to be a valid inequality, and that is because both x1 and x2 are non-negative. So if we take a smaller multiple of x1 and a smaller multiple of x2, we're certainly not going to make it larger than what it was. Okay, so because x1 and x2 are non-negative, well, in this case only x1, we can round down 2 to 2. Well, that doesn't bring much new. And 1 over 63, that's 0 rounded down, right? So we get plus 0 x2 is less than or equal to the same value, 121 divided by 21, is valid because x2 must be greater than or equal to 0. So far, just a revision from last week. What was the next trick? The next trick was, because this is an integer, it's one next to it to be integer, well, this is 0 anyway, 2 times an integer must be an integer. And it's less than or equal to something that is less than 6. So it must be less than 6. So if it's less than 6 and it's an integer, it cannot be more than 5. Okay, so 2x1 is less than or equal to 5 is a valid inequality as well. Because integer. Can actually improve this one. Yeah, you see the improvement. You're nodding. How do we improve this? Yeah.
Change the 5 to a 4.
Yeah, we can in fact change the 5 to a 4 because if you divide it, this means that x1 is no more than 5 halves. And because x1 is integer still, and it's less than or equal to 2.5, it cannot be more than 2 is also valid. Is this clear? The idea? Yeah. Okay. So this is called a Chvátal-Gomory procedure. Gomory, I don't know. Chvátal, I know he drinks a lot. He made me skip some talks at the conference. He wanted to go to the pub. About 70 now. Okay, so they invented this kind of procedure where you take linear combinations, round down the coefficients, and then you can round down the right-hand side. And any questions? Oh no, it's on YouTube. I shouldn't be saying things like that. Okay, never mind. I have no notes for this slide. So, yeah, so the importance of that procedure that we've just seen is that if you keep repeating it, eventually you get any valid inequality. So it's good. So if you know that procedure, you know everything. You don't need anything else. Great news. But the problem is, where do I get the numbers, the 2/7 and whatever over whatever that I started with? And the answer is here. Okay, so let's say I'm trying to solve this problem. Simple problem, and we've seen picture and we've seen everything. So how do I solve it? Well, I first solve the LP relaxation. That's always a good idea, because if the solution happens to be all integers, that's not the solution, that's the initial tableau. So if the solution happens to be all integers in the LP relaxation, where I forget the integrality, then I've already solved the problem and there's nothing else to do. And so I'm happy. So how do I solve LP relaxations? Well, in practice, normally you don't do it by hand, but the computer does it internally. And it does it by doing the simplex method. Okay, so it starts with a tableau. That's just the initial tableau. I don't know why I put it there. But what's important is it ends with a final tableau. Okay. Like this. Now, you can see the solution is not all integers. X1 is non-integer. S3 is non-integer. So that's bad. But what is each row in a simplex tableau? A linear equation. And it's a linear equation which, moreover, is a sort of linear combination of the constraints that we started with. So in particular, solutions satisfy all the solutions, even the integer ones, will satisfy. Well, feasible solution satisfies what? That if I'm looking at this row, I get x1 plus 1/7 s1 plus 2/7 s2 is equal to 27. Do you agree? Yeah, that's what the simplex tableau does. And so, it also satisfies this, doesn't it? X1 plus 1/7 S1 plus 2/7 S2 is less than or equal to 20/7. Do you agree? Well, it's equal, so it certainly is less than or equal to. So this is a valid inequality. So now I can do my trick. What's the coefficient of x1? 1. Rounded down, still 1. Okay, x1. For s1, it's 1 over 7. Rounded down, 0. 2 7s, rounded down, 0. Okay, so they go to 0, and this is less than or equal to 27 is a valid inequality. And because x1 is integer, I can round down the 27th to, I think that is just under 3, so that rounds down to 2. So that's about how it works. You know from the first tableau how to express S1 in terms of x1 and x2. Because S1 is the difference between the left-hand side and right-hand side. S2 here as well. So if you substitute it for x1 and x2, there you get the constraint which is only in x1 and x2. And it would be some linear combination of the original inequalities. You don't have to do it now because you get it from the tableau like that. So once you get it, if you're trying to solve it just by these cuts, they're called cuts in planes, what you do next is you just add this as a constraint into that tableau. That goes back to how we were doing, adding a new constraint into an optimal tableau. So if you do that, it looks like this. So you have a new constraint, the right-hand side is 2, x1 is 1 there, and everything else is 0 times there. And S4 you get is a new slack variable. I guess it looks like this. Is that what you expected? Okay. Except this is not a simplex tableau, so this is new non-tableau. Because it only becomes a tableau when you do the row reduction. So you have to, yeah. You know what I mean? So in the tableau you want a 0 here, because the next one is in the basis. What you need to do is take this row, subtract from that row, you get the actual tableau. And apparently, what you get is this minus 607. I'm doing it too fast. I'll soon run out of things that I want to talk about today. And then students will sue me that they're not getting the money's worth from the university. I will have to pay everybody £5 back or something. Okay, what do you do with a tableau like this? You know that. First, you say anything? Opening your mouth without dual pivot? Yeah. Yeah, so you need to do a dual pivot somewhere because of this negative value. And when you do, I think, yeah, apparently there's only one. You get this tableau. That look good? That does look good because now we found the optimal solution. An optimal solution. We don't know if there are any other ones, but well, one of them is this one. So x1 is 2, and x2 is 3, and the objective is 9, and the problem has been solved. Okay, the advantage of oh, what have I done? Okay, so what happens when you do it from a simplex tableau like this is one important thing. Okay, I'll go back to that tableau. Is it this? Is this what I want? Is that when you start with a fractional row in the tableau like this, you start with one that is not fractional, then you're not getting anything. But if you start with one which is fractional, then you get a constraint, this one, or even, yeah, this one, which is not satisfied by the original solution. Okay? It will never be, because of the way this works, this optimal solution to the relaxation is not going to satisfy that constraint. So you'll always have to do the dual pivot. So you're always getting somehow closer to the actual integer optimal solution that you want. You always cut off somewhere. It's a basic property of this. So it's part of the assignment that you have, J4, is it gives you the optimal tableau for the problem that you're asked to solve using branch and bound for the relaxation. And you're supposed to use this procedure for any of the, whichever row you pick, the non-integral rows there are from 2, so you pick one of them. And you're now dividing the inequality like this. And then you should also check that the optimal solution that you get from here, so something that will be there, does not satisfy this constraint. Okay, just to Okay. One more thing that I forgot to do is I'll try to do it. Now watch the beauty. Now the question is, why should I pick this road and not that road? And we don't really know which one to pick. Okay? Each of them will work. So let's have a look at this one now. Just because we can. Just because I want to show you something. Okay, so this row is minus 2 over 7 S1 plus 10 over 7 S2 plus S3 is equal to 23 over 7. Okay, so rounding down, what do we get? Minus S1, 10 over 7, rounds down to 1, doesn't it? So plus S2 plus S3 is less than or equal to, and rounding down the right-hand side, it's just over 3, so rounds down to 3. Do you agree? No? I did all the steps in one now. Hopefully everybody is okay with that. Now, this is nice, but sometimes I would like to know what it means for the x's and for the x's. For the x's. Okay? How do I find out what it means for the x's? I go one slide back. No. 2. This equation tells me what S1 is. This equation tells me what S2 is, and this equation tells me what S3 is. So I can substitute. So if I do that, okay, so what is S1? Can't remember. Apparently it's 14 minus 7x1 plus 2x2. Are you checking it? Yeah? S2 is 3 minus x2. And S3 is what? 3 minus 2x1 plus 2x2. Yeah. So this is less than or equal to 3. And so what you're supposed to get from that is that 5x1 minus x2 is less than or equal to 11. So this one is not as good, right? But you never know. Why is it not as good? Yeah, so if x1 is no more than 2, as we had before, then this can't be, so this is also satisfied. If you get no more than 10, you take away something. The other one was better. Everything that satisfies the previous one also satisfies this one. So this one. So in that case, it was better to take the x1 row than the s3 row, where you never know really.
I'll just put a note, not as good as x1, less than root 2.
One more than that. Okay, so when you're doing the actual solving thing in tableaus and adding new inequalities, you don't have to go from here to there, because this can also be added into the tableau. So you just have -1, 1, 1, and the new s4, and that's just as good. You don't have to add this. You can add that directly into the final tableau. So, yeah. Now, any questions? It's too easy. So let's see how you do on the homework.
Just to summarize, there is this slide in the last one.
Is, the whole algorithm works like this. Solve the LP relaxation. If the solution is integral, that's it. You're done. Otherwise, you find a non-integer row in the tableau. Do the trick with the rounding down of things. Add a new constraint, a new row in the tableau. The tableau becomes infeasible. If it doesn't become infeasible, you don't have to do dual pivoting and you've made a mistake. Do dual pivoting, you find a new optimal solution. If it's all integer, then you're happy. Otherwise, choose a row which is not integer and go on and on and on. So you've solved it. It will solve it eventually, but you never know how long it's going to take. That's everything. Thank you for coming. Is there any more questions? Oh. Now you can fully solve both my assignments because Mosul is easy and now you know how to finish off AF4 as well. Time for a cup of tea.